Stars are like cosmic chefs, cooking up light in the biggest ovens in the universe. But instead of gas burners, they use nuclear fusion. Today, we're sneaking into these celestial kitchens to uncover their explosive recipes for light. Let's zoom into the heart of a star. Imagine the most extreme pressure cooker you've ever seen, cranked up to about 15 million degrees. Here in the core, hydrogen atoms are literally being squished together so hard they merge into helium. It's like cosmic bumper cars, but instead of just bouncing off each other, these hydrogen atoms stick together and create something totally new. Every second, our sun transforms 600 million tons of hydrogen into helium. And here's the wild part. Some of that mass turns into pure energy, which bounces around inside the star like a pinball before finally breaking free as light. That's right. The sunlight warming your face started as hydrogen getting smooshed together in the sun's core. Let's talk ingredients. Stars might seem super complicated, but they actually start with a pretty simple shopping list. Hydrogen is the star of the show, pun totally intended. Think of it as the flour in your cosmic cake recipe. It's the basic building block that everything else comes from. When you pack enough hydrogen together, gravity starts playing chef, squeezing these atoms so tight they have no choice but to combine. And what do you get? Helium. It's like hydrogen atoms giving each other such a big hug they become something completely different. But here's the cool part. This cooking process isn't perfect. Some of the ingredients escape as pure energy, and that's exactly what we see as starlight. Wild, right? Okay, let's map out a star's temperature zones. And trust me, this is way more extreme than your kitchen's hot and cold spots. The surface of our sun is already a whopping 10,000 degrees, hot enough to turn iron into vapor instantly. But that's actually the star's cool zone. As we dive deeper, things get seriously spicy. The middle layer hits about 2.7 million degrees, but the core, that's where the real heat party happens. We're talking 27 million degrees Fahrenheit. It's like comparing a matchstick to a nuclear explosion. At these ridiculous temperatures, atoms literally can't keep their cool. They're zooming around so fast and crashing into each other with such force that nuclear fusion becomes inevitable. This temperature gradient isn't just for show. It's absolutely crucial for moving energy from the core to the surface. Let's talk about the real MVP of star cooking, gravity. Imagine you're squeezing a stress ball, except this stress ball is the size of 1,000,000 Earths, and you're squeezing it with the force of 1,000,000,000 hydraulic presses. That's basically what gravity does to stars. It's constantly crushing everything toward the center with such incredible force that atoms can't help but slam into each other. Without this cosmic pressure cooker effect, stars would just be giant clouds of lazy gas floating through space. But gravity turns them into fusion powerhouses. The pressure at the sun's core is about 250 billion times what we feel at Earth's surface. It's like having the weight of 250 billion atmospheres crushing down on every square inch. That's the kind of pressure it takes to cook up some starlight. Here's where things get really crazy. That energy from the core has to fight its way to the surface, and it's not exactly a straight shot. When light is born in the core, it starts an epic journey that can take up to 100,000 years. Yeah, you heard that right. The photons bounce around like they're in the world's longest pinball game, bumping into countless atoms on their way up. They zigzag through the star's layers, getting absorbed and re-emitted over and over. It's like trying to walk through a packed concert crowd, except this crowd is made of super hot plasma and stretches for hundreds of thousands of miles. By the time that light finally bursts free from the surface, it's probably forgotten all about its wild journey through the star's interior. Stars come in more flavors than your local ice cream shop. Let's meet two of the most fascinating types, red giants and white dwarfs. Red giants are like stars having a midlife crisis. They've puffed up to massive sizes, turning red and cooler. Well, cooler for a star, still hot enough to vaporize your entire neighborhood. Think of our sun swelling up so big it could swallow Earth. White dwarfs, on the other hand, are the retired veterans of the cosmos. They're super dense, incredibly hot, but tiny, about Earth-sized. Imagine squeezing the mass of our sun into something the size of our planet. That's like cramming 1,000,000 elephants into a matchbox. These cosmic opposites show us just how wild a star's life can get. Stars don't last forever. They eventually run out of their favorite snack, hydrogen. Think of it like a cosmic food truck that's running low on ingredients. When a star like our sun burns through its hydrogen stash, which takes billions of years, so no need to panic, it starts getting creative with its cooking. It switches to helium fusion, which is like upgrading from a regular stove to a super-powered furnace. The star puffs up like a giant cosmic soufflé, turning into a red giant. But here's the thing. This is basically the star's last-ditch effort to keep the party going. Eventually, it'll run out of fuel completely, toss its outer layers into space like a frustrated chef, and shrink down into a white dwarf. It's the ultimate kitchen cleanup. Our sun is like that perfect bowl of porridge from Goldilocks. Not too hot, not too cold, just right. At about 4.6 billion years old, it's in its stable middle age, pumping out energy at exactly the rate Earth needs. The sun's mass is crucial here. With 333,000 times more stuff than Earth, it has just enough gravitational muscle to maintain steady fusion without going overboard. If it were just 20% smaller, we'd be cosmic popsicles, and if it were 20% bigger, well, let's just say Earth would make a great sauna. Plus, our sun's kitchen timer is set perfectly. It'll keep cooking steadily for another 5 billion years, giving life plenty of time to do its thing. Let's talk about when stars have their ultimate kitchen meltdowns. Some stars don't just burn out quietly. They go out with a bang so massive it outshines entire galaxies. Imagine a cosmic pressure cooker exploding with the force of 1 billion nuclear bombs. That's a supernova for you. These stellar explosions happen when massive stars can't handle their own cooking anymore. Their cores collapse faster than a failed soufflé, while their outer layers blast off into space at millions of miles per hour. But it's not all drama. These explosions are actually cosmic recycling programs, spewing out elements like iron, gold, and silver into space. That's right. The bling on your finger probably came from an ancient star's kitchen disaster. The stars aren't just one-trick ponies in the kitchen of the cosmos. They're constantly cooking up new elements. Think of it as the ultimate cooking show where each new recipe creates heavier elements. Iron, nickel, gold. They all come from stars experimenting with different fusion recipes. The really massive stars are like master chefs, capable of cooking up elements all the way to iron in their cores. But here's the mind-blowing part. It takes the explosive finale of a supernova to create elements heavier than iron. That's right, every gold ring and silver necklace exists because some ancient star went out with a bang. These stellar kitchens are still at work today, constantly adding new ingredients to our cosmic pantry. Thanks for joining me on this stellar cooking adventure. Now you know stars are the ultimate cosmic chefs. If you enjoyed this kitchen tour of the universe, smash that like button, hit subscribe, and share with your space-loving friends. See you next time.